Okay, good. Let us begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for these students. We thank you for homework, which is super fun. Pray that you'd help us to understand the next topic, which is integration, that you be glorified, Lord, and we do this day. In your name I pray, Lord Jesus. Amen. All right. So, today we will start talking about multivariate integration. So my goal today is to describe to you the definition, all right? And I tell you what, I'll even start with a little numerical calculation. So here's the problem. We'll start with a problem. Estimate the volume bounded by z equals to f of xy, and let's let f of xy equal to 4 minus x squared minus y squared on the, well, let's say over, and let's say 0 less than or equal to x less than or equal to 1, or let's not say 1, let's say 2, and 0 less than or equal to y less than or equal to 2. So I'd like to estimate the volume of that thing. Let me try to draw a picture of what we're doing. So what is z equals to 4 minus x squared minus y squared? It's one of these deals, right? Oh, and one other thing. I need a that's the top, and that would give us a side, but let's say z equals to 0. Okay, so here's the z-axis, here's the y-axis, here's the x-axis, and basically what we're doing is we're just looking at sort of a chunk of this graph, right? And then this is where I have trouble. Nah, that's not quite right. I mean, it's some kind of, I don't have a clear picture of what that would look like in my mind. I'm not happy about this picture. Let me try again. So it's something like I mean, this isn't quite right. I mean, oops, I think I made this. Try again. I'll get it right eventually. I don't know. I'm trying to, that's still not right. Give me a second here. I'll eventually get like I want. I mean, it's kind of square, right? So something like that is this. So the top, right, the top here is z equals to 4 minus x squared minus y squared. And then I'm only looking at between, let's see, this would be what? What's this here? So here's like the 2, here's 2, right? This point would be what? This point would be 2, 2, 0. Yep.
Is it 2, 2, 0 on your original function?
Uh-oh. I think Luke has a good point. What's 4 minus 4 minus 4? What should we do to make this picture make more sense? Because I am not giving up on this picture. It's my third attempt at a stupid picture here. How about this? Let's take this 4 and make it like an 8, a 10 rather. If I make that a 10, that's still probably not enough. I probably should do something like 20. That's probably more accurate to the picture. All right, so the top thing here, which I will outline in green shortly, this right here, what's this point right there? 2 what? I do 20 minus 4 minus 4, yeah, 12. Okay, so. And let's figure out a few more points. What's the value of the graph right there at that point right here? Let's see, that would be 2, 0, 16. And how about this point over here? Also 0, 2, 16, right? What's this point up here, the highest point? 0, 0, 20, right? And how about a middle point, right in the middle, right above this? One 18. Very good. So if I wanted to approximate the volume under this curved surface, what could I do? I could kind of use some like rectangular solids to kind of approximate it. Think about it like, I could take this curved building and replace it with 4 kind of boring skyscrapers, let's say. And let's see here. You could make maybe one like, I don't know, like this. Right, and then I could choose this next one to be based on the height of the middle box. Like that, right? And let's see here. And then I guess I could do this one based on that point, right? And then I guess I could take this one back here based on that point, right? I don't know if this probably is not a very great picture, but oh well. Sorry, I tried. I tried. Okay, but anyway, let's say that this is 1, 2, 3, and 4. What would the volume of 1? So the volume of 1 plus the volume of 2 plus the volume of 3 plus the volume of 4 would be equal to what? Maybe you can improve on my picture. I'm sure you could. So what do I need? I need the area. I need the area times the height, right? So like 1, what's the area of each one of these? I set it up to be 1, right? So the height of the first approximating, rectangle, well, not rectangle, but rectangular solid is what? Let's say box. The first approximating box, box 1, has area 1 and height what? I use the middle point as its height, right? So 18. So I get 18 plus what? Now 2, what's the height of 2? 16. What's the height of 3? 16 again. And what's the height of the back one? 20, right? So this, what do you think? Would this be an overestimate or an underestimate? See, I'm not really sure, right? Because I have 3 of the, well, I don't know, these guys, right? These ones here, underestimates, but the other ones are overestimates. So maybe it's, I don't know, I'm not sure which, I can't tell without doing a deeper analysis whether it's an overestimate or underestimate. It ought to be kind of sort of close. What's the value? What is that? 70, all right. And of course, this is an approximation. So the idea here, though, is very simple, really. Each one of these boxes, what we're doing is we're taking the value of the function at some sort of sample point, let's say x sub a, x sub I, y sub j, and we're multiplying by the area, which you could say change in x times change in y. And I don't need an x sub I and a y sub I there. I don't need indices for the change in x and change in y, provided what? Provided I use a regular grid. I use the same displacement in x and the same displacement in y for each approximating rectangle, right? But that's the volume of the ijth box, really, right? It's something like that. And so what you do is, if you're trying to find the volume bounded by some function, right, over some rectangular region, you just take the rectangular region and chop it up into little boxes, right? Make a grid, and then just sample the value of the function at one point on each little rectangle. Add those all up together, and that should give you the net volume, right? An approximation. So an approximation then would be something like some I equals 1 to n, some j equals 1 to m of f of x sub I, y sub j. And really, we should kind of like choose those randomly. So you might say bar or something, just to say it's some kind of random sample point in the ijth region, and then delta x, delta y. This is an approximation of the area bounded by the graph. Now, to be more specific, I have in mind. Oh, I'm sorry. I'm using the thing that doesn't show up in that silly video. So I have in mind something like. So you might want to zoom in on this, otherwise it won't show up, unfortunately. So I have in mind some sort of region where we're, say, going from like, let's see, the points here would be something like A, C. Over here you have A, or rather BC. This point, I would say, is B comma D. This point here would be B comma, oh, I'm sorry, yeah, A comma, what did you say to me? A comma D? Right. And so this would be for the inequalities what? So if I'm trying to find the volume over this rectangle where we're bounding x between a and b, and we're bounding y between c and d, I look at this rectangle, I think about chopping it into a fine rectangular grid like this, right? So this maybe is the ijth one. Subrectangle, I should say. And so, I mean, for this contains, what does it contain? It contains the point x sub I, x sub bar I, y sub bar j, all right? So how would we, that would give me a really decent approximation for the volume that is, well, if f is positive, right? If f is positive, then it gives me a good approximation to the volume between z equals 0 and z equals f of xy on that over that rectangle, right? And then how do you make it exact? How do you get exactly the volume? What do you do? Oh, one other thing. What's delta x? What's delta y? Divided by what? Yeah, which one goes with which? So the j is attached to the y. So that means m goes with the d and c, right? M as in mummy, and n as in nanu nanu goes with the other one here. There you go. So in other words, there are m divisions this way, and there are n divisions that way. So if I want exactly the volume, I just take the limit as m and n both go to infinity of the sum I comma j equals 1 to m and n. Well, fine. So that would be the, a pretty, well, not a pretty good, that would be exactly the volume. In fact, I would use this to define volume, frankly. So what I'm showing you, of course, is just the bivariate generalization of the Riemann sum, right? Do you guys remember this from when we did integrals before? We talked about Riemann sum and take the limit as the number of approximating rectangles goes to infinity. That gives you what? The area under the curve. Here it gives us the volume under the graph, assuming what? Assuming the function's positive. And so this this is also the definition, in fact, of the integral over the rectangle R, double integral of f of xy dA. So there you go. That is the definition of the double integral. Now, I have been saying that f is positive in order to make the identification with volume, right? But what would it mean if f was negative in this sum? I mean, actually, if you think about it, what it calculates is what's called the signed volume, where you're counting volume below the xy axis is negative, and counting volume above the xy axis is positive, right? In fact, we already encountered that by accident in my first example with my first choice of having 4 here. You see we had a negative value. This graph actually crossed the xy axis. We would have gotten a negative value for this for the first approximating box if I had left it and not changed that to 20 to make it more natural. So generally speaking, the double integral can be negative. It could be 0 because it's not just a volume, it's actually calculating signed volume. Now there's another way you could think about it. Instead of thinking of this as being, calculating volume, you could think of this as adding together the mass of something. You could think about this grid as actually some sort of laminate, some sort of like two-dimensional thing with variable density, right? And what's density? Mass density, right? So if this had mass density, what's mass density in this context? It's the little bit of mass and the little bit of area. So mass per unit area. If you take mass per unit area, so this is usually called sigma. So what happens if you take sigma times a little delta A, a little change in A? Well, that gives you the amount of mass in that little rectangle. So another way we could think about this is we're adding together, to think of this, you could think of this as like dm dA times dA, so it gives you dm. This is a way of adding up all the little dm's, all the little bits of mass over the grid, and so that would give you the net mass. So you don't have to interpret the double integral as a volume. You could also interpret it as the integral of a density, where this would be giving you the net mass over that rectangle. Does that make sense? Or it could be charge per unit area. This would give you the net charge in this little rectangle. Are we good? Yeah.
Does that R mean anything in particular that we should know at this point?
Oh, yes. This whole thing is R. R is the rectangle. Sorry. If you want me to be more pedantic about it, R is equal to, thank you, Luke, that's a very good question, xy such that A less than or equal to x less than or equal to b, comma, y less than or equal to, oh, idiot, c less than or equal to y less than or equal to d. Now, there are a number of problems in your book that get you in touch with your inner summation notation calculator. I mean, there's a nice selection of problems to try to make that more meaningful to you, the actual process of calculating a double summation, right? But I'm not going to go into that in here because actually part of the beauty of Calculus 3 is the fact that while this is the basic concept that underlies the double integral, in terms of actual computation, we don't have to calculate these sums. Isn't that good news? Right? Just like in the Calculus 1 when you learn the fundamental theorem of calculus, which basically says what? The integral is defined in terms of a summation, right? But we actually don't have to do that sum explicitly, thank God, right? Because the summation is very hard, right? So there's a theorem that I will tell you now because I think it's time for us to do it. And this is not a theorem I prove, it's just a theorem I state. And it states the following: if I want to integrate over the rectangle like I just have there, f of xy dA, then in fact that is equal to the integral from a to b, parentheses, the integral from c to d, f of x comma y dy, parentheses, dx. So this, on the left-hand side, we have I'm talking about the double integral as we just defined over here. On the right-hand side, I have a derived result. This is a theorem that states that you can, in fact, calculate this double integral in terms of what's known an iterated integral. So this is an iterated integral. Before too long, most of you will probably, whether you realize it or not, think of that thing on the right as the definition of the double integral. But you should remember that at its base, it's something more directly geometric. So this expression here actually is all things we already know how to do. Because we know how to integrate, right? And then we know how to integrate again. And we've already been doing integrals with respect to one variable holding the other fixed in our calculation of potential functions, right? So let's take this theorem out for a spin. Let's see how it does on a numerical example. Let's see if we were right or wrong about the 70. Can I erase this because it takes me a lot of work to get this back? If you got a question about it, ask it now. All right. What have we learned so far? Double integral can calculate the signed volume over a given region, but it can also calculate the net quantity of something if f is the density of that quantity over the region. All right. So again, but with theorem. So we want to calculate the integral over this rectangle. Oh, the rectangle is actually what? It's a square. You could write it as 0, 2 squared. This is a silly notation for 0, 2, Cartesian product with 0, 2. Anyway, it's this square is the rectangle of consideration, right? What's the integrand? 4, oops, sorry. You guys gotta, come on guys. When I do this, do fuss at me. I should make this a 20 as well, right? Why didn't you guys fuss at me?
I meant to, and then you said something new. I scrambled to write it down and I forgot.
Oh, okay. I'm just saying, it's never too late to fuss at me for something like that, all right? Well, there is one time it's too late when I erase it. So, yeah. Okay, so 20. Minus x squared minus y squared dA. So allegedly that's the integral from 0 to 2, the integral from 0 to 2 of 20 minus x squared minus y squared. And I wrote it over here as dy dx. By the way, the theorem also says that you could do it this way. You got choices, either x first or y first. Now, sometimes that's the difference between being able to calculate it or not being able to calculate it. All right, so you guys, what do you want me to do first, x or y on this one? All right, I'll take you up on that, x. So then I put these parentheses in at the start. Think of them as training wheels. We will take them off eventually. Okay, integral from 0 to 2. What's the integral of this with respect to x? It is 20x minus 1/3 x cubed minus xy squared. I take that, I evaluate from 0 to 2 because that's the fundamental theorem of calculus. Let's see here. So what do we got? We got 40 minus 1/3. Oh, sorry. It's sometimes a good idea to write 2 equals to x and x equal to 0 to remind yourself what you're doing. Talking to myself at the moment. So yeah, this first one evaluates to 40, right? And then what? Yeah, minus 8/3. Yeah, minus 2y squared. Let's see, that's that's what? That's 120 minus 8, 112 thirds. What's 112 thirds? It doesn't, okay. Integral from 0 to 2, 112 over 3 minus 2y squared. Okay, so we can, that's 112 over 3 times 2 minus 2/3 of 8. Is that 66? Oh, okay, okay. Oh, yeah, 28. What did you say it again? 69.3333. Okay. Hey, not too shabby. The point of this was not that you should try to do multivariate integrals that way. I mean, to be clear, this is your course, right? I mean, so this is your life. This would be your job if you were a person who did numerical methods for some industry or something. You might actually, well, you might not actually have a formula. You might only have a set of data. And so you might use that set of data to set up a multivariate integration just numerically. Then you have to take this approach, right? suppose you don't have a formula, all you have is a data set. All you can do is this idea, right? But since we have a formula, we can find antiderivatives and use theory and find nice numbers like this with a lot less work. I guess about the same work, I don't know. Questions?
Well, it depends on how much accuracy.
Mm-hmm. What's the accuracy of our second approach? How accurate is this? 100%, right? Yeah, it's it. It's exact, right? Okay, let's do another example. Actually, I think I don't need to do more examples of this. Honestly, anyone here not understand what I just did? There's plenty of topics that are harder. We should spend our time on examples for those topics, right? So I'll do a triple integral here shortly. How about that? Yep.
Would it change at all if you did it like dy versus dx?
No, that's the cool thing is it wouldn't matter if I did dy first. I mean, we could do that. So if I had done y first, I would have got integral from 0 to 2 of what? If this integrates with, in fact, it's, oh, this is really, this problem is, you could argue that it has to be the same by symmetry in this problem. That's not generally the case. That's not generally the reason that these are equal. I don't think. Well, that's an interesting question. But, I mean, you see where it's going. This would be 20y minus, yx squared minus 1/3 y cubed evaluated from 0 to 2 dx and dot, 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 dot. I mean, it's actually the same stupid thing here. Yeah, if you just, exactly, if you just switch x and y here, you get the same answer.
It's sort of like two
Even
triangles.
if they were like different bounds, it wouldn't matter.
That's, yeah, let's look at a different example because that's just a coincidence here.
It's sort of like taking,
Yeah?
it's sort of like having two different right triangles that share the same hypotenuse.
Yeah.
I mean, to get from point A to point B following that hypotenuse,
Uh-huh.
you're going to take different paths, but you'll still get the same.
Right, right. True.
Do we need to put units in our
No. We don't work with units in here. I mean, I suppose technically it depends on the units of the integrand. If the units of the integrand are coulombs per square meter and x and y are in meters, then the answer is in coulombs. If f is if f is kilograms, and if f is kittens per square inch, and x and y are in inches, then it gives you the number of kittens. I mean, I don't know. We leave those considerations to another course. Let me come back to the exchange symmetry with a slightly different example. I want to make sure I get this in today. The triple integral over some box of a function of 3 variables. What would that be defined as? Limit it as, let's say, m, n, and l go to infinity of the sum I equals 1 to m, sum j equals 1 to n, sum k equals 1 to l of what? Of f of x sub I, y sub j, z sub k, delta x, delta y, delta z. Don't make me try to draw the picture for this. I can't visualize what this means directly. Right? I mean, I could think about it being the volume under some sort of graph of a function of 3 variables, but that's a 4-dimensional comment. What I can tell you is whatever this is, it's calculating, we can think of it in terms of density, right? If F is, say, mass per unit volume, this is calculating the net mass in the box B, right? And I say it's a box, but it really could be a blob, right? And I said R was a rectangle, but if you think about it, you could just as well have it be some sort of curved linear, some kind of curved linear smudge. As long as you can chop that up into little squares, you can add up the, little rectangles, you can add up the value over those rectangles and get the thing. It's just, we can do the calculation most nicely when it's when this B is actually one of these guys. Right? If it's this, then I can do the calculation easy peasy. So let's suppose A is less than or equal to X is less than or equal to B, C less than or equal to Y less than or equal to D, E less than or equal to Z less than or equal to G. I already used F. Then there's a theorem that says I can do this as integral A to B, integral C to D, integral E to G of f of x, y, z. And then here's where you got to be careful. When you do these iterated integrals, the dz and the dx and the dy, they have to be paired in the logical order with the bounds. That's the most important new thing here. You notice that it goes inside out. Like this gets paired with that. 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 See, x goes from A to B. Y goes from C to D. So that's why there has to be this linking. So the same pattern over here, what do I have to do first? What goes from E to G? Z, right? So I do dz. And then this is this one. So I go dy. And finally, the last one, right? Dx. Bless you. And so this is actually a method with which we can actually calculate these integrals. So let me show you an example. Now, Christina's concern has gotten so much worse now. Now instead of having just two ways, is it yx or is it xy? Now we've got x then y then z, y then x then z, y then z then x, z then y then x. There's 6 of them if you count track of them. I lost track of which one I said already. But there's 6 possibilities, 6 possible iterations. They're all, it won't matter which order you do it in these rectangular ones. But let's look at a specific one. How about the integral from 0 to 1, integral from 0 to 2, integral from 0 to 3 of y. We'll do dx, dy, dz. So this would be, of course, the integral, triple integral over this rectangular box, right? Which is what it's got a 1, 2. Yeah, I'm trying to think which length has which side. If I'm drawing in the usual x, y, z way, So the height of this box is what? It's 1. The y is the 2, and the x is the 3. Yeah.
So the flip x on you when you label the box.
Oh. Thank you. You're right. So this, yeah. Okay, so let's do the calculation. So, I hope this should be the easier part of this. Let's see, when you integrate y with respect to x, what happens? You get xy, right? And we have to evaluate that from x equals to 0 to x equals to 3. Then that is taken over dy, and that is taken over dz. Okay, so the first integral gives us actually what? Just what? 3y. What's the integral of 3y dy? y, you say y squared evaluated from 0 to 2? Yeah. Oh, thank you. Which is what?
6.
All right, so 6 dz. 6. So let's look at this a different way. Let's do the y integral first instead of the x integral first. See what I did? I flipped these differentials dx and dy to dy dx, and I have to correspondingly flip the bounds. See that? So what do we get? Yes, 6. I mean, we will get 6, I hope, but let's work it out. The first integral is what? What do we have? 1/2 y squared evaluated from 0 to 2 dx dz. What's that? That gives us what? Integral from 0 to 1, integral from 0 to 3 of what is this? 2. So I get integral from 0 to 1 of 2 times x evaluated from 0 to 3 dy, which is integral from 0 to 1 of 6 dy. Oh, yeah, thank you. Z. So what do we get? 6. Now, it may be too soon for me to tell you guys this. Maybe it's too soon. But there's something really neat in terms of the calculation here. If you have an integral like this, you can simplify it in the following way. You can go, okay, so I can really rewrite this as the integral from 0 to 1 of what is it? dz times the integral from 0 to 2 of y dy times the integral from 0 to 3 of dx. In fact, this kind of integral you can write as just a multiplication of ordinary integrals. That's only possible when the bounds are nice, they're just constant bounds, and also the integrand, you can factor it into functions of just x, functions of just y, functions of just z. Like, as another example of that, if I had the integral from, say, 0 to 1, 0 to 2, 0 to 3 of x, y squared, z cubed dz, it is in fact true that that integral can be calculated in a very nice, simple way. You can calculate this, well, as the integral, let's see here. Oh, I'm sorry. I should say, what, dx, dy, dz? Okay. So you can actually calculate this one by the x dx integrates from 0 to 1, multiplied by integral from 0 to 2, what's the y? Y squared dy times the integral from 0 to 3 of z to z. Thank you, z cubed, yeah. So the answer is 1/2 times 8/3 times 81/4. By the way, that is enough work to show in here for those kinds of integrals. That's about as much work as I will be showing as we go further. This isn't calculus 1 anymore. We do integrals faster. Which is the principal stumbling block for you guys following along in the next few lectures. So, but I would encourage you that you could iterate these integrals like we were doing and get the same answer. That is, in fact, the case here. All right, so with that, I will shut up. Have a good evening. Thank you for your